Welcome to the General Chemistry 1 Visual Labs at the University of St. Thomas. Today's lab is about Lewis dot structure and molecular orbital theory. The purpose of this lab is to become proficient at drawing Lewis dot structures for molecules. You will determine the electronic and molecular geometries, as well as polarity and the molecular orbital hybridization. A Lewis dot structure is a representation of valence electrons in a compound structure. For example, this is the structure of cyanic acid. The hydrogen atom and carbon atom share a single bond, which is one pair of shared electrons. The carbon atom and nitrogen atom share a triple bond, which is three pairs of shared electrons. And there is a lone pair of electrons on the nitrogen atom. Now let's define electronic and molecular geometry. Electronic geometry can be determined by the number of electron groups around the central atom. This includes lone pair electrons. Molecular geometry can be determined by the number of bonds around the central atom. As you can see on the slide, this is the structure of water. The electronic geometry of water would be tetrahedral because there are 4 electron groups around the central atom oxygen. The molecular geometry would be bent because there are 2 bonds around the central atom. Now let's talk about hybridization. Molecular hybrid orbitals include sp, sp2, sp3, sp3d, and sp3d2. All of these orbitals match the number of electron groups. For example, the hybridization of H2O is sp3. Because there are 4 electron groups. So how do we know if a molecule is nonpolar or polar? Well, the polarity of a molecule is determined by examining the individual bond dipole moments. So for nonpolar molecules, they have individual bond dipole moments that cancel. But in polar molecules, the dipole moments of the individual electron groups do not cancel. At the bottom of the slide, we have CO2. CO2 has no net dipole since each dipole moment cancels out. Therefore, CO2 is a nonpolar molecule. On the other side, we have HCN. HCN has a net dipole. Therefore, it is a polar molecule. Resonance structures can also represent Lewis dot structures. They show the delocalization of electrons. The double-headed arrow between the structures show that the actual structure of the molecule is somewhere between the resonance structures. For part 1 of this lab, you will fill out the table as shown. You are given a compound and you will draw the Lewis dot structure of the compound. You will determine the hybridization, electronic geometry, molecular geometry, and also determine if the molecule is polar or nonpolar. We will go through some examples to show you how to fill out the table. For part 1, the first example we will go over is HCN. The Lewis dot structure of HCN is shown on the table. The hybridization of the molecule is sp. The electronic geometry is linear because there are 2 electron groups. The molecular geometry is also linear because there are 2 bonding groups. HCN is polar because there is a net dipole. Next example we will go over is H2O. The Lewis dot structure of H2O is shown on the table. The hybridization is sp3. The electronic geometry of the molecule is tetrahedral because there are 4 electron groups. The molecular geometry is bent because there are 2 bonding groups and 2 lone pairs of electrons. H2O is polar because there is a net dipole. The last example we will go over is C2H4, also known as ethylene. The Lewis dot structure shown on the table is the entire molecule of ethylene. If we split the molecule in half at the double bond, you will see that the carbons will separate. If we focus on one carbon on the left, the hybridization would be sp2. The electronic geometry of one side would be trigonal planar because there are 3 electron groups. The molecular geometry would be trigonal planar because there are 3 bonding groups. The entire molecule of ethylene would be nonpolar because there is no net dipole. Here are the other molecules that are needed in order to complete the table. You may pause the video if you need more time to view the molecules.